The 1930s saw the birth of a revolutionary theory, quantum mechanics. This theory sought to explain the strange behavior of light and matter at the atomic level. However, early versions of quantum mechanics faced a major problem. When applied to certain phenomena, like the interaction of light and electrons, the theory predicted nonsensical infinite values. This was a crisis. Physicists knew something was amiss. They needed a new understanding to resolve these contradictions. The problem lay in how physicists calculated the probabilities of quantum events. These calculations involve interactions between particles, such as the emission and absorption of light by electrons. However, existing methods failed to account for the countless ways these interactions could occur, leading to infinite results. The infinities plagued some of the brightest minds in physics. Werner Heisenberg, one of the pioneers of quantum mechanics, even doubted the theory's validity. He wrote, "The saddest chapter in modern physics is and remains the theory of quantum electrodynamics." Clearly a breakthrough was needed. The stage was set for a new generation of physicists to tackle this challenge. They would need to develop radical new approaches to tame the infinities and unlock the secrets of the quantum world. Little did they know, a revolution was about to unfold. Richard Feynman, a young and unconventional physicist at Cornell University, was among those determined to solve the quantum puzzle. Feynman was known for his playful nature and unorthodox thinking. He approached physics with a contagious enthusiasm and a deep intuition for the natural world. Feynman's breakthrough came in the form of a radical new approach to quantum mechanics, the path integral formulation. This method, inspired by earlier work of Paul Dirac, offered a completely different way to visualize and calculate quantum processes. Imagine a particle traveling from point A to point B. Classical physics tells us it will take the shortest, most direct path. Feynman's approach, however, embraced the strangeness of the quantum world. He imagined the particle simultaneously exploring every possible path connecting the 2 points, no matter how improbable. Each path, no matter how strange, contributed to the probability of the particle's journey. Feynman developed a mathematical tool, the path integral, to sum up the contributions from all possible paths. This approach, though mathematically daunting, offered a powerful new way to understand quantum phenomena. While Feynman was developing his path integrals, other physicists were independently tackling the quantum puzzle. Julian Schwinger, a brilliant and mathematically rigorous physicist at Harvard University, took a different route. Known for his formidable intellect and elegant equations, Schwinger developed a sophisticated approach called renormalization. Schwinger's method systematically identified and removed the infinities plaguing quantum calculations. He achieved this by carefully redefining the parameters of the theory, such as the mass and charge of the electron. This process, though mathematically complex, yielded remarkably accurate predictions for experimental observations. Meanwhile, in Japan, Shin'ichirō Tomonaga was developing his own approach to quantum electrodynamics. Working in relative isolation during World War II, Tomonaga devised a method known as the interaction picture. This approach focused on the interactions between particles and fields, providing another successful path to taming the infinities. In 1947, a historic conference took place on Shelter Island, New York. This gathering brought together the leading minds in physics, including Feynman, Schwinger, and Oppenheimer, to discuss the latest developments in quantum mechanics. The conference was electric with anticipation. The attendees knew they were on the verge of a major breakthrough. At the conference, Feynman presented his path integral approach, while Schwinger outlined his renormalization technique. The initial reaction was one of confusion. Feynman's diagrams, with their strange loops and squiggles, seemed like child's play compared to Schwinger's dense equations. However, as the discussions continued, the power and equivalence of the different approaches became clear. Despite their contrasting styles, Feynman, Schwinger, and Tomonaga had independently arrived at the same solution. The infinities that had plagued quantum theory were finally being tamed. Section 5. Taming Infinity. The key insight that emerged from Shelter Island, and later refined by Freeman Dyson, was the concept of renormalization. This technique involved absorbing the troublesome infinities into the parameters of the theory. Instead of trying to calculate these parameters from first principles, physicists realized they could be determined experimentally. The success of renormalization lay in its ability to separate the infinities from the physical predictions of the theory. By carefully redefining the parameters, physicists could isolate and discard the infinite contributions, leaving behind finite and meaningful results. This was a profound shift in thinking. It allowed physicists to sidestep the thorny issue of the infinities and focus on making accurate predictions. Section 6. Drawing the quantum world. Feynman's path integral formulation, though mathematically equivalent to other approaches, offered a particularly intuitive way to visualize quantum processes. Feynman realized that his path integrals could be represented graphically using simple diagrams that have become iconic in modern physics. In a Feynman diagram, particles are represented by lines, while interactions between particles are depicted as vertices where the lines meet. For example, the emission of a photon by an electron is represented by a vertex with one electron line entering and two lines leaving, one electron line and one photon line. These diagrams provided a powerful tool for calculating the probabilities of complex quantum processes. By drawing all possible Feynman diagrams for a given interaction, physicists could easily visualize and calculate the contributions from different quantum paths. The diagrams simplified complex calculations, making quantum electrodynamics accessible to a wider audience. Section 7. QED, a triumph of prediction. The theory that emerged from these breakthroughs, known as quantum electrodynamics, or QED, stands as one of the most successful theories in the history of physics. QED describes the interaction of light and matter with astonishing precision. Its predictions have been experimentally verified to an accuracy of 1 part in a billion. The triumph of QED lies not only in its accuracy, but also in its wide range of applications. QED provides the foundation for our understanding of a vast array of phenomena, from the behavior of atoms and molecules to the interaction of light with matter in lasers and transistors. One of the most striking predictions of QED is the existence of antimatter. According to QED, every particle has an antiparticle with the same mass but opposite charge. For example, the antiparticle of the electron is the positron. The discovery of the positron in 1932 provided strong experimental support for QED. Section 8. The legacy of light. The development of QED had a profound impact on physics, extending far beyond the realm of light and matter. It provided a blueprint for understanding other fundamental forces of nature, leading to the development of the Standard Model of particle physics. The Standard Model, which describes all known elementary particles and their interactions, is a triumph of 20th century physics. It incorporates QED as a cornerstone and has successfully predicted the existence of new particles such as the Higgs boson, which was discovered in 2012. The legacy of QED extends beyond its predictive power. It represents a triumph of human ingenuity and collaboration. Feynman, Schwinger, and Tomonaga, each with their unique perspectives and approaches, collectively solved one of the most challenging problems in physics. Their work serves as a testament to the power of human curiosity and the importance of collaboration in scientific discovery. Section 9. Beyond the horizon. Despite its success, QED is not the final word in our understanding of the universe. It leaves some fundamental questions unanswered, such as the nature of dark matter and dark energy, which together make up 95% of the universe's energy content. Furthermore, QED does not incorporate gravity, the force that governs the large-scale structure of the universe. Unifying QED with Einstein's theory of general relativity remains one of the biggest challenges in modern physics. The quest to understand the universe continues. Physicists are constantly exploring new frontiers, seeking to uncover deeper truths about the nature of reality. The story of QED, with its twists, turns, and ultimate triumph, serves as an inspiration for the next generation of physicists as they grapple with the mysteries that lie ahead. The universe is vast and full of wonders, and the journey of discovery is far from over.